Hey guys, so today's gonna be mostly the same, but a little bit different. Because I have something cool to show you. I wouldn't say I'm a gamer because I'm not a gamer, but I do have a few games that I've played and I like a lot. So I'm gonna show you one of them today. I promise it relates to chemistry. It actually does. So here's the game. It's called The Binding of Isaac. After Birth Plus, which is just so appropriate as I'm sitting here just super pregnant. And the premise of the game is kind of a weird game. So the idea is that it's based off of the Bible, sort of. And the story of Isaac in the Bible is that, I don't know the whole story, but I think it was that God commanded Isaac's dad that he needed to kill Isaac, and that's pretty much as far as it goes for the simile. But the idea is that I'm playing as a character named Isaac, and my mother, instead of father, is trying to sacrifice me. So I'm trying to get away. But I'm very, very sad at this event that I have a mom who is trying to kill me. And so let's see, let's do a new run. I'll play as Isaac. Okay, so I'm really, really sad about the fact that my mother is trying to kill me. So basically my only weapon here is that I shoot tears because I am so sad. I can move around and shoot tears, and that's about it. You understand the idea? Okay. Sorry about that pause. I changed the settings so that maybe hopefully you could see the screen a little bit better. Okay, so here we go into a room. The screen's really not that much better, but anyway, here we go. Okay, so I'm going into all the rooms and I can collect the items, and I'm really not trying to do that. I'm just trying to find a room. There we go, with some enemies. These are little pieces of poo-poo that I'm going to be, oh, I got hit. Okay, and there we go. Okay, you get the prize, go to the next room, and you get the idea. So the whole point of this, I'm really trying to find like a specific enemy. I might just have to play until I find it, and then I'll unpause the video here. The biggest idea is that Isaac shoots his tears at a very consistent rate. Like I'm just holding down I'm just holding down the button, just holding it. And you can see it's like pew, 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 like very consistent at that rate, or I can shoot in this direction. But look at the spacing between them. The spacing, I mean, they do kind of like it falls to the ground at the end, but the actual spacing, if I were to measure the distance, it's very consistent, right? Like I keep my fingers the same amount of space and whoop, whoop. Cool. Now watch this. If I start walking forwards though, while I'm shooting tears, do you see how they get like crammed together there? Like look, oof, they got all squishy. Or if I'm shooting to the right and I walk to the left, look at how far apart those tears get. You see? Oh, whoops, wrong row. Oopsies. So when I'm walking forward, they get smooshed together. When I walk away, they get farther apart. But the whole time, they're still shooting at the same speed. Shoot, 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 shoot. It just depends on if I'm walking in the same direction or, whoopsies, same direction or reverse direction. You're like, oh gosh, this is so boring. Okay, I love this game and it's gonna be hard to pull me away from it. Okay, I'll just die. It's fine. Oh no. I'm gonna get okay. So what I usually do when I play is I do this. I move back and forth and I try and like get a bunch of them to hit the enemy all at once. So the whole point of that is just if I'm shooting forwards, bloop, 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 and I'm going towards you, the tiers are going to get more compact because not only am I shooting them forward, but I'm walking forward. Yeah. If I'm shooting forward, but walking backwards, even if I'm blinking at the same time, it will spread out as I'm going away and push the tiers together as I'm going closer towards you. And this game, The Binding of Isaac, is like the only example that I can like find on how to like easily show students what I mean by that. So with that in mind, what we're going to do today is actual science. And we're going to work on the last part of Unit 3, which is emission spectra. So pull that out and we'll work on that. So here's what the homework looks like. And right away, I'm noticing that I've got the stripe barcodes and they each correspond to like the different elements. And you should know why at this point, different elements have different stripe patterns. So number one, let me pull the first page out of my packet. Number one says below, bright line spectral charts, aka bar graphs, are shown for 5 elements. That's a lie. 1, 2, 3, 4, 5, 6. It's actually for 6 elements, but that's okay. And 4 unknown samples. List all of the elements that are present in each unknown sample. So if this is what lithium looks like, lithium has a stripe here, a stripe here, a stripe here, and a stripe here. I'm going to use that information to see, is lithium in any of these samples down here, these unknown mixtures. So here's what I recommend. Don't just try and eyeball this like straight down, because some of the lines get really close to each other. So I'm going to recommend you get like a ruler or a separate sheet of paper or whatever. I'm going to use a sticky note. And I'm going to see which ones I can find to see if it has lithium in it. So here's the line for lithium, and I'm doing my bestest to keep it straight. And it looks like I do have a couple of them that would have lithium in it, specifically here and here line up with that stripe for lithium. I need to check and make sure all 4 stripes are there. So checking, and I probably won't underline it for every single one of them, but these ones line up. Next set. Yep, there they are. Lined up, and lined up. So, boop, 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 boop. These were the stripes that I would expect to see for lithium. They are in unknown X. Lithium is present. Lithium is also present in sample Y. I don't know what else is there yet, but I know that lithium is in at least those samples. And it's important to check all 4 of them, because look, if I didn't check all 4, I might get thrown off by this line here and be like, oh yeah, look, lithium, lithium, lithium all the way, baby, except for it's not, because this stripe, which is also a lithium stripe, isn't showing up. So make sure that you check all of the lines when you're trying to decide what's in something. I'm thinking, here's a dead giveaway. I'm thinking right here, this double stripe thing going on here, cha. And that's pretty unique. But, you know, check everything, make sure everything lines up. Potassium also has, let's see, a double stripe there and there. which matches. So this sample is lithium and potassium mixed together. Does that make sense? Here's how you do number 1. You'll go through and list what's present in the mixtures. So that is more of last time stuff. But what I want to get into is this thing called shift. So flip to the back side here. And number 7 says the diagram below shows a standard spectrum compared to one produced from a distant star. What conclusion can be made by comparing the standard spectrum to the spectrum produced by the distant star? So this weird thing happens if we're looking at, let's say, just an example. I don't know what element this is, but the Powerpuff Girls were created by chemical X, so I'll just use that as my example. Chemical X. And if chemical X has on Earth a spectrum that looks like this, kind of 3 here and 2 there, it's going to have that same pattern even if it's on some distant planet or a distant star. However, notice that it's gotten a little bit shifted. We still have 3 stripes and 2 stripes, but if I like connect them, let's see, that color. This color. Okay. You should just get a ruler for today. You probably will need it. So see, those stripes have shifted this way, and also both of these two stripes have shifted that way. They've shifted more towards the infrared side, not the ultraviolet side. And you're like, okay, cool, so what? So when they're in space, they're a little bit off. What's your point? My point is, we're actually going to talk about the Big Bang Theory. Because, scratch paper here, just like my little Isaac guy, when he's sad and he's crying in this direction, when he's just standing there, the tears come out at that consistent rate. If Isaac starts moving this way, it's going to appear that the tears are more and more compact because he's moving in the same direction. We call this blue shifting. Isaac's tears are blue shifted because they seem more compact due to Isaac walking towards whatever he's walking at. The opposite is if Isaac started to walk, I don't know, this way. Bad guys are over here. So he's walking away from the enemy. His tears, if we were to measure them, are going to look further apart. They're going to be spaced further apart. He's not actually crying at a different speed. It's just if the tears are more compact or if they are more spread out. The spread outness is due to him moving away from what he's shooting. This is called redshift. So redshift is when something is walking away from you, still shooting you, but walking away. Blue shift is they're walking towards you and shooting you. More compact, more spread out. So instead of Isaac, let's say Actually, I'm gonna leave this out here. Let's pretend that instead of these being Isaac, these are stars. Here's a star. Here's a star. I'm not gonna worry about that. Everything in the galaxy is moving. It's either moving towards us or away from us. We're over here on planet Earth. In example 1, we're here on Earth and we're looking into space. We're looking to see what is our favorite star doing. It's sending back light, not tears, but light that we can see. If the light is more spread out than it should be, we're going to assume that our star planet is moving away from us. That makes sense? So instead of Isaac shooting tears at an enemy, we, our Earth, our other planet, is sending back light, because stars are just flaming orbs of light in the sky. They're sending back light. And if it's more spread out than it should be, that means that the planet or the star is moving away from us. If we look and check on our favorite star and say, hey star, how you doing? You still glowing so brightly? And it is more compact, boop, 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 than it should be. And we're like, whoa, your light is like way more compact. You must be moving towards Earth. Redshift, blue shift. So back to the original problem, you can use light and you can use the stripe patterns from the light to determine if something is coming towards you or again, or like away from you. So on Earth, we think the stripes should be here. Since it shifted more towards infrared, we're going to say this light has been red shifted because it went more that way. Okay, now, every year a student always asks, so if it goes more towards infrared, then it's red shifted. How come when it goes more towards ultraviolet, it's not violet shifted? The answer is, I don't know. It's like a Dr. Seuss book, 1 shift, 2 shift, red shift, blue shift would be if we went that way. Towards purple. I know, I get it. It's weird. So this light is red shifted. Back to my little example, if something is red shifted, it means that it's moving away from us. So the star that we're looking at is sending us light while walking away from us. So our options include, okay, what conclusion can we make? Read all the options. Which one looks best? I'm going to cross out the ones that say the star is moving away from Earth, because that's not true. Oh, wait, is it true? Hold on, let me think. No, those ones are true. We're going to keep that one. It is moving away from Earth. My bad. It is moving away from Earth. So we've still got option B, and we've still got option D. Those are looking solid. Towards the Earth would be blue shifted. So I'm going to get rid of those two. And now I just have to find the difference between B and D. So B says, the star's spectral lines have shifted towards the ultraviolet end. Nope, they went towards infrared. So that's not true. Ooh. The star's lines have shifted towards the infrared end. So the star is moving away from Earth. Cool. So there we go. The reason that this is significant is back to our Earth and star example. Backside? Sure, backside of paper. Here's somewhat a disturbing thought. Here we are on planet Earth with people living all around. There are stars in every direction all around us in the galaxy. Do you like my artwork? I'm gonna start up a DeviantArt page for this amazingness. And all of the stars are sending back light. But here's what's crazy. When we check out this star, to us, it looks redshifted. When we check out this star over here, redshifted, redshifted, redshifted. It doesn't matter what way we look into the universe. I mean, you could probably find one that's like on a collision course with us, but the majority of the light that we see on Earth is redshifted. That means that everything around us is currently moving away from us, getting farther and farther and farther and farther away. So in a million bajillion years, if all of our stars keep moving away from us, you're going to look up, okay, you'll be dead, but theoretically, you'd look up into the night sky, and as far as we'd be able to see, we wouldn't be able to see stars anymore because they all like moved away. That's kind of crazy pants. So where am I rambling on with this too? If currently everything in our universe is moving away, think backwards, then a long time ago, it was closer. So going backwards in time, things were closer and closer and closer and closer. So if things were very, very close a long, long time ago, and they're now expanding, the universe is expanding, that's evidence for what we call the Big Bang. And that's not to say that you can't have any other belief system necessarily. It's just the universe is expanding, and whatever point that happened, whether we don't even know why or what caused it, but for whatever reason, deity or otherwise, when Earth and the galaxies began to expand, that's what we call the Big Bang. So we can actually use chemistry to prove the Big Bang, which is really cool. So number 2, according to the Big Bang theory, which graph best represents the relationship between time and size of the universe? So what this one is saying is from beginning to the end, the size of the universe has stayed the same. And that's wrong. This one is saying that the universe was really, really small, and then it got big at some point, and now we're back to nothing. Our universe is nothing. Doubt. Other options include that it started out really big. We just said it. No. So the only other option is that the Earth started out, not the Earth, the universe started out small and it's continuing to expand. As time goes on, we expect it will expand even more. The theory that the universe is expanding is supported by, not that, we haven't even talked about that. We haven't even talked about this either, none of this stuff. Your choices are redshift or blue shift. Which one is evidence that stuff is moving away from us? Okay. Number 4 is like the same exact question. That's cool. So just same answer twice, and then you'll get like extra points. Woohoo! The more that the spectral lines of a star are shifted towards the red means, and then you've got some choices here. Don't overthink it. You only know that red shifting has something to do with the object moving away. So keep that in mind. The velocity of a star, how fast it's moving, either towards or away from Earth, can be measured by, again, your answer should probably include something about shifting and shifting the lines. And the last one that I'm going to help you with, because you're going to do number 9 on your own. You're going to do number 10 on your own. It's more analysis of the graphs. A new police officer on his first day of work is unsure why his radar is not working to determine the speeds of the passing cars. He is parked at the side of the road. Okay, so here he is. There's his car and there's his wheels, and he's there. Perpendicular to the direction of traffic. So he's facing this way. And here's the road. And it says that he's trying to determine the speed of the cars as they pass him. So as the car's like, meep, meep, and then as it passes him going this way, he's like, bam, with the radar and tries to see the speed. Explain why this method isn't working. Well, the idea of a radar is the same principle that we're using for our shift. So you can determine the speed of something, the velocity of something moving towards or away from you can be determined by measuring the shift in light that you're measuring. Since the car's not really moving towards or away from him because he's lined up perpendicular to the road. What he needs to do instead is not park here, park anywhere else that's the same direction, either forwards or backwards. Either would be fine, because then as the car is coming, you can measure the compression or expansion of the light, but it only works if you are parallel to the radar. So something about that make it look a little nicer than my explanation here. The bottom problems. So what we're doing here is you're going to decide which diagram, option 1, 2, or 3, matches this element. So here's your OG, there's your OG stripe pattern. Which one of these options makes the most sense when the star is moving away versus moving towards? And the bottom one is asking, similar to question 1, you have a mixture of elements with these stripes. And I'm wondering like which ones are in there, and explaining why, no matter how much of a scoop you have of element Z, it's going to look the same exact stripes as 2 grams of Z. Is the amount of Z relevant to the striping? The answer is no. But you're going to explain that in your problem.